everyone to the third of the HiPACC summer schools. What I wanted to do in this lecture is talk a little bit about the organization that's sponsoring these summer schools, the High Performance AstroComputing Center at the University of California, and talk a bit about the challenges to astronomical computation. Good morning, Trudy. Lots of good seats to go. And then at the end of the talk, talk a bit about cosmological visualizations. And I'm expecting that I'll get through all of this in less than an hour, but I'm not sure because in the middle I'm going to have, after more people have arrived, I was going to spend a few minutes on some organizational questions. Anyway, if we finish early, I'll start tomorrow's talk, which I'm hoping to have time to do. So I realize this is hard to read. All of the slides are going to be posted right after the talks on the HiPACC website. And in addition, all of the talks are being video recorded. And we'll try to post the videos in a fairly short time. And eventually they'll all get posted. So take notes, but appreciate that all of this material will be available. So 3 years ago, there was a competition in the University of California to start new institutes that combine at least several campuses, sometimes the entire University of California system. So I wrote a proposal where I said the stuff that's on this slide: as computing and observational power continue to increase rapidly, the most difficult problems in astrophysics are now coming within reach of simulations based on solid physics, including the formation and evolution of stars, planets, and supermassive black holes and their interactions with their galactic environments. The purpose of the High Performance AstroComputing Center is to realize the full potential of the University of California's world-leading computational astrophysicists, including those of the affiliated national laboratories. That's the DOE laboratories at Berkeley, that's the Lawrence Berkeley National Laboratory, Lawrence Livermore National Laboratory, and Los Alamos, that's Los Alamos National Lab. HiPACC will do this by fostering their interaction with each other and with the rapidly increasing observational data, and by empowering them to utilize efficiently the new supercomputers with hundreds of thousands and now millions of processors, both to understand astrophysical processes through simulation and to analyze the petabytes and soon exabytes of data that will flow from the new telescopes and supercomputers. And then the bottom is about our outreach efforts, which include developing educational materials, publicity of websites, and distribution of simulation outputs, including visualizations that are beautiful as well as educational. So I'll have some examples of those, especially in my talk tomorrow. This is the organization of HiPACC. I'm the director. There's a coordinator from Northern California, that's Peter Nugent, who heads the computational astrophysics group at Lawrence Berkeley Lab, and Mike Norman, who is our host here. I haven't seen Mike yet this morning, but I'm expecting that he'll be here soon. So he's the director of the San Diego Supercomputer Center and one of the founders of modern computational astrophysics. The other people listed are from each of the institutions that I mentioned, the national labs and the UC campuses. And there's HiPACC staff. Sue Grasso, could you stand up, Sue, so everybody knows you? So it's very important that you get to know Sue if you want to get reimbursed. Now, the bad news about reimbursement for travel, so first of course, all of the dormitory expenses are covered by HiPACC. The bad news about getting reimbursed for travel expenses is that we submitted, Mike Norman and I, a proposal to the National Science Foundation months ago, asking for $20,000, which is in line with what they've given us before, and we just aren't hearing. Now, this is fairly typical for the National Science Foundation. Some of you probably have heard about this sort of thing. We're still hopeful. We didn't hear no, but we just don't know yet. So what's going to happen is that Sue is going to ask you to fill out forms so that if we get the National Science Foundation money, we will be able to reimburse at least a fraction of your travel expenses. The other people here, there's actually fourth person here, are Nina McCurdy, and Nina's standing over there in that corner. And Nina's the webmaster. She's done a great deal of visualization work, and she's also going to help coordinate this summer school in that she'll be collecting all of the talks to post them quickly and also helping the speakers with any of these audiovisual materials. Trudy Bell, who's sitting right up in front, is the senior writer for HiPACC. Trudy was an editor of Scientific American for 6 years. She was the founding editor of Omni magazine. She was an editor. She was, I guess, a senior editor at IEEE Spectrum, which is the magazine that all the electronic engineers get for 14 years. And Trudy's written a dozen books, published hundreds of articles about astronomy and about computing, and won many, many prizes for her journalism. And in the back, just stepped out for a moment, is Will Felker, and Will is going to be recording all the lectures on video. So those are HiPACC staff people. So HiPACC has funding opportunities, and this is particularly relevant for people from the University of California. Small travel grants, grants of up to $5,000 to support working groups or participation in scientific meetings. We're currently supporting one of these, combining people at UC Irvine and UC Davis, for example. Mini conference grants, we do several of those per year, as you'll see. Grants to faculty to support AstroComputing summer research projects for undergraduates. We were doing a number of those this summer. We did some last summer. Matching grants of up to $10,000 for AstroComputing equipment. We supported several of those. And basically, we invite people to submit proposals in all areas that we haven't thought of and will consider them. The budget of HiPACC is $350,000 a year from the University of California. You may have heard that the University of California is broke. It's true. Nevertheless, the University of California still is supporting some of these interesting, innovative projects. Incidentally, I was told that my proposal to start HiPACC was ranked number 2 of all the proposals submitted. So it was quite popular. So we do annual conferences in Northern and Southern California. We have these international astrocomputing summer schools. The 2010 school was at the University of California, Santa Cruz, my home campus, on hydrodynamic galaxy simulations. Hi to 3 or 4 people here who were also at Santa Cruz. Last summer, it was at Berkeley and Lawrence Berkeley Lab on computational explosive astrophysics, novae, supernovae, gamma ray bursts, binary mergers, etc. And the 2012 school, of course, is here. And as it says at the bottom, we have some funding from the Department of Energy, which is to pay costs here, basically. And we're still waiting to learn whether NSF will fund our proposal. So this was the meeting that we held here at the San Diego Supercomputer Center in December 2010. It's called The Future of Astrocomputing. This was the Northern California meeting in 2011. It's called the Santa Cruz Galaxy Workshop. Every summer for many years we've had a conference on galaxies at Santa Cruz for 1 week by invitation. And this year we've already had the Baryon Cycle Conference in Irvine last month, June 14, 15, 16. And we'll again have the Galaxy Workshop at Santa Cruz. Of course, we're having the summer school now. We had a computational astronomy journalism bootcamp, and there were 20 journalists selected from more who applied. Several foreign ones, journalists from the Los Angeles Times, the main science magazines, including Scientific American, Sky and Telescope, and so forth. That was at Santa Cruz, but with a field trip to NASA Ames Research Center and to the California Academy of Sciences in San Francisco. And we're going to be sponsoring a high-resolution galaxy simulations workshop in Santa Cruz just after this summer's Santa Cruz Galaxy Workshop. That's for all of the groups that are doing high-resolution hydro simulations of galaxies, simulations with
better than 100 parsec resolution, preferably much better. And several of the people here are going to be also participating in that. Essentially, all the groups in the world that are doing such simulations are going to be represented. And the idea of this meeting is to kick off at least a year-long comparison project that will go beyond what people have done so far and try to really understand, as well as we can, what the simulations are doing, how they're doing it, why they aren't doing it better, and how well it compares to the observations. So that was the 2010 summer school. This was the poster for the 2011 summer school. Trudy, you have to give me some pictures from the 2011 one. We should post them on our website. So that's the one in Berkeley last summer on computational explosive astrophysics, as this thing says. Incidentally, the person who makes these beautiful posters, including the one for this year's school, is Nina McCurdy. So this is the poster that presumably you've all seen advertising this school. So at one point we had 41 students, but 4 have canceled, including, I think, 2 at the last minute. So I think it's now 37. As you know, that's the schedule. So I'll go till 9:30 plus 10 minutes for discussion. Then there'll be a break. Then Alex Zale, and then Matt Turk. Then we're having lunch at 2 different places. One's called the Bistro, and the other one's called the Great Hall. And they're both within a short walk from here. And you've all received maps, right? Yes? Okay, good. So, and maybe we can get some local person to help to guide us at least the first day. Now, I wanted to, at this point, talk a little bit about the plan for Sunday. So, there are half a dozen great Shakespeare festivals in the United States, which are not just Shakespeare. They do other people's plays as well. But the Old Globe in San Diego is certainly one of the really great ones. Hi, Mike. So this is Mike Norman, the director of the San Diego Supercomputer Center and also a lecturer at the school. One of Shakespeare's greatest plays is Richard III, the deformed last of the York dynasty of kings, who it's certainly he's one of Shakespeare's greatest heroes, except what he's really great at is being evil. So these are taken from 2 reviews of the current production. So this one starts, "Now is the winter of our discontent made glorious summer by this son of York. J. Whittaker screams his first entrance as Richard III with such strained ferocity," because those are the words, "you'd think his audience sat across Balboa Park in the Starlight Bowl." The Globe is set in this beautiful downtown park called Balboa Park, where there are something like 14 museums, nice hiking trails, lots of restaurants and things like that. It's clearly, Richard III is the big hit of the summer at the Shakespeare Festival. Continuing from the review, "For Richard III, Shakespeare wrote a star vehicle for a black hole. Richard boasts that he will woo and wed Lady Anne, whose husband and father Richard has slain. And he does it in one of theater's most brilliant scenes. He systematically eliminates whoever stands in line. In the end, no one will come to his aid, not even a horse." So, of course, that's the famous line, "My kingdom for a horse." "The title character of Richard III is one of the most diabolical and outrageous villains in all of literature. A ruthless Machiavellian, the brilliant and power-hungry lord embarks on a bloody campaign to seize and keep the English crown. Shakespeare paints an unforgettable portrait of his obsession, seduction, betrayal, and a man who would be king." And Whittaker is a famous actor who's starred in lots of these kinds of productions. The play is directed by Lindsay Posner, The festival is headed by the person who ran the Royal Shakespeare Festival in England for 11 years. He just recently came to San Diego, and he now heads the Old Globe. So the plan is, you've paid a registration fee, and that covers the snacks and the lunches, but it also has money for an excursion. And the plan is that the excursion will be that everybody gets picked up here at your dorms on Sunday at roughly 1 o'clock, although that may get adjusted. We might decide to include a box lunch and leave earlier. And then first stop, Birch Aquarium. It's a beautiful, very nice, small aquarium associated with the Scripps Institute of Oceanography, which is part of UC San Diego. But it's far enough from campus that you probably wouldn't get there unless we took you there. And then onward to Balboa Park. And the plan is to get to Balboa Park pretty early, like 3 o'clock. So you have lots of time to visit museums if you want, or just hike around the park, or yourself. Dinner will be provided at a restaurant in the park, and then admissions to the play, and it turns out we can still get good seats for Sunday night. It's an outdoor theater, so bring a jacket, and then the bus will take everybody back. Now, crucial question, because we need to make plans for this, how many people would like to go on the tour? Please. One. Okay, actually, well, no, I think keep your hands up so that we can count, because we need to do is make plans for the bus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I got 32. Oh, I'm sorry. Okay, could everybody raise your hands again? Sorry. So, Sue, can you do an independent count and see what you get? No, because there's a maximum on a bus. It turns out the biggest bus we can get is 36. Okay, great. So no problem. We can fit on the bus. We have plenty of money for the tickets. So great. So we're going to make plans, and of course, if somebody changes your mind, there'll be room for a few more people or a few fewer people. But we do need to buy the Shakespeare tickets today. So that's why I needed to interrupt this lecture on galaxies and cosmology and big data and things like that to tell you about Shakespeare's greatest villain. His second greatest villain, incidentally, is Iago from Othello. Okay, now back to the subject of this week, and next week for that matter, big data and astronomy. So there are lots and lots of illustrations of the data issues in astronomy, and I just picked this one because I happen to have this figure readily available. So what this is the HiPACC downloads. HiPACC is the NASA infrared database, and this only goes to the middle of 2011. But the main thing that you see is that there's been a huge climb. So in this database right now, there's 200 terabytes of data. Sorry, that's not right now. That was as of a year ago. Since then, the WISE data has been added, which, I don't know, probably doubles it. And WISE is the Wide Field Infrared Space Explorer, or something like that. Anyway, we had, 30 years ago, a satellite called IRAS that was essentially a single pixel map of the sky in the infrared. Extremely useful. This is a much better instrument, WISE. It's a many pixel, something like 1 million, map of the entire sky in, I think it's 3 infrared bands. And all of that data, of course, is public. And the red here is the Spitzer data. Spitzer is space telescope in the infrared that has several different instruments. All of its data is publicly archived, and that's most of the 200 terabytes that they had as of last year. And as you see, the rate of downloads has increased a lot. But that scale of data, and you'll hear lots more about data on the scale of hundreds of terabytes, is nothing compared to what's coming down the pike. In particular, Andy Connolly, I think he's lecturing mostly next week, is going to talk a lot about the plans for the Large Synoptic Survey Telescope, LSST, which will deliver time domain coverage for orders of magnitude more objects. Basically the entire southern hemisphere. It's going to be located in Chile. It's envisioned that this project will produce about 30 terabytes of data each night for 10 years. The final image archive will be about 70 petabytes, possibly much more. And the final LST astronomical object catalog is expected to be 10 to 20 petabytes. Of course, a petabyte is 1,000 terabytes. An exabyte is 1,000 petabytes. LSST's most remarkable data product will be a 10-year movie of the entire southern sky. This time-lapse coverage of the night sky will open up time domain astronomy. So, as you know, we've been discovering a few hundred supernovae per year. LSST will discover 1,000 new supernovae every night. It's a completely new scale. And this is just one of a number of big data projects that are coming down the pike. So, astronomy is one of the areas that's leading the way into this new environment where we're going to have a huge amount of data. And the challenge is going to be to make sense of it and use it. Now, there's a second thing, which is a great challenge to astrophysics, and that's the changing nature of the computational environment. These are graphs from a report that came out last year on the future of computing from the National Academy of Sciences. These are actually from the appendix. And what they show is the processor performance and the processor clock speed. And what you see is that processor performance, this is for individual central processing units, CPUs, was climbing in terms of number of operations per second steadily up until about 2004. And then it's still climbing, well, for the 8 years since then, but at a slower rate. So that we're now about 10 times below what the processor speed would have been if it had stayed on the previous track. And in 2020, we'll be 100 times below. Now, does that mean that computers are slower? Well, no. It just means that the clock speed has basically plateaued at about 3 gigahertz. The reason is that to operate computers at higher speed, it's perfectly possible, but it takes a lot more energy. And the energy requirements have begun to be very severe. Computers are now using, I forget, 2 or 3% of the entire United States production of electricity. And if it had kept increasing, doubling every year or two, then clearly we would really be up against the wall. So the computer manufacturer, and of course it also means that we would have had to pay a lot for just the power. That's ultimately going to be the most expensive part of computing. So the result has been that the computer manufacturers have changed the way they design the machines to have lots of cores on a chip and only use the ones you need, and to have new kinds of devices that are much more efficient in both data processing capability and energy use than traditional CPUs. In particular, the millions of gamers have been buying machines that have powerful graphic processing units, GPUs. And current GPUs have the equivalent of thousands of cores and can do many vector-type operations. So if you take the dot product of two vectors, you multiply, vector 1, item 1 by vector 2, item 1, and then add that to vector 1, item 2 times vector 2, item 2, and then so on. That's a vector operation. And that's the kind of thing that these GPUs do extremely efficiently, because that's the sort of thing you need to do if you're going to move pixels around on a screen. So you can now buy a top-of-the-line GPU for a couple $1,000 which is much faster than the top-of-the-line Cray of 10 years ago, which cost $20 or $30 million. So the result is that people are now putting on individual nodes on supercomputers, lots of memory, several multi-core chips with dozens or more cores accessing that memory, and a big GPU that typically is 10 times as fast as all the cores put together, but only for doing certain operations. So the result is that you have to program these machines in a completely new way. You can't, the old style was you basically write single processor programs and you spread them around using MPI. And you have to occasionally worry about balancing the load. But it was a simple way to program compared to these new machines, which really require a subtle knowledge of how the computer works. Because, of course, the nodes have to communicate with each other and draw data from across the system. So I've had some experience doing this kind of programming, and it's really difficult. And in fact, there's a new system of the type I described, 64 nodes, 48 gigs of RAM each. Each one has 12 double-threaded cores, 2 Westmere chips, plus a Tesla 2090, which was last year's top-of-the-line NVIDIA GPU. So there's 64 nodes like this, and my team has actually been, this is Chris Moody. Chris, raise your hand. And Patrick Janssen, who did the original programming. We've been essentially the sole users of this powerful system at NASA Ames because nobody else has figured out how to program it. And they won't let you use it unless you can show that you're using it efficiently. If we don't turn on the graphic processor unit, the system runs 12 times slower. The graphic processor unit speeds the entire calculation up by a factor of more than 10. Something we had demonstrated back in 2010 when we first learned how to program this kind of thing. But it's not easy. So the result is that there are 2 big challenges facing computational astrophysics. One is the big data challenge. Data that's too large to move. The data is going to typically sit on one or a small number of machines, petabytes, ultimately exabytes. The pipes that move the data haven't been getting any bigger. Or rather, they've been getting bigger arithmetically, but the data's been increasing logarithmically, exponentially. So faster, larger computer outputs, more powerful observations, these gigapixel cameras, taking many pictures per night, and falling storage costs. And the changing high-performance computer architecture from network single processors to multi-core GPUs and even fancier things that are going to be coming along. So these challenges demand new collaborations between natural scientists and computer scientists to develop tools and scientific programmers to convert legacy code and write new codes efficient on multi-core and GPU architectures, including fault tolerance and automatic load balancing. One of the most challenging problems is that as you try to do some big computation, the different parts of the computer can finish their job at different times, and so you get a lot of latency. A lot of the computer is waiting for some small part to finish because the load has been very imbalanced. And what's needed is compilers that will generate automatic load rebalancing instructions. And to my knowledge, this doesn't exist yet. And of course, as we go from hundreds of thousands of cores to many of cores, it's inevitable that we're going to have some loss of computational power during big computations. And so we have to figure out how to have fault tolerance. We need new ways to visualize and analyze big data, especially remotely. The old style was that you do your observation, you take the data home to your workstation, and you process it yourself with your team, your graduate students or whatever. And the new system is, first of all, you can't move it. Second of all, you couldn't store it even if you could move it, because you're talking about huge amounts of data. Many, many terabytes now, petabytes soon. And so what we're going to have to do is learn how to ask questions to the remote machines and get back answers rather than data. Now, of course, that's the style that Google and certain other companies have pioneered. They never give you their data. They wouldn't dream of it. They just give you answers, which is, after all, what you want. So what we have to do is learn how to think about astronomical data, including output from simulations, that way. We have to train new generations of scientific computer users and improve education and outreach. These are the challenges to the field. Now, astronomy is special in a number of ways in this challenge of computation and big data. The data tends to be pretty clean. The data is mostly non-proprietary. NASA insists that raw data be made public on a fairly short time scale, and most astronomers have switched from the old mode where you publish lots of papers, but you never make the data available until no one's interested anymore, to basically making data available very quickly as soon as your team has had a chance to at least look at it, and sometimes even before that. The research is mostly funded, and the data is pretty sexy. That is, people find it very interesting. And the fact that people find it very interesting is illustrated by projects like Galaxy Zoo, where there's 100,000 volunteers who classify galaxies. They've been mostly working on nearby galaxies, and they're starting to get, I think they're getting tired of the nearby galaxies, which are basically a combination of disks and spheroids, of course. And that they basically are supposed to say whether it's mostly a disk or mostly a spheroid. As you go out to higher redshift, the resolution is poor. The galaxies look much more complicated. I'll show you some examples next lecture, and I'm sure you'll see others. And so what we're doing is we're starting to feed them multicolor images. I think the protocols have now been pretty much worked out. They want 3-color images that are made from mid-optical to something like 1.6 microns. So mid-IR, near IR. And they want to classify those. And meanwhile, there are people working directly with the Hubble Space Telescope data that are doing their own classification. But it's going to be interesting to work with the Galaxy Zoo people as well. One of my colleagues at Santa Cruz, Greg Laughlin, who's now the chairman of the astronomy department, created Transit Search, which basically makes data available as soon as it's acquired from the several different kinds of projects that look for planets around other stars. And it's basically raw data, and with lots of program tools that help people analyze the data. And the game is to see if you can figure out the nature of extrasolar planetary systems from whatever data is available, fitting multiple planets and so forth. And of course, SETI at home. And there's many other examples of public involvement involving, in this case, 100,000 people. SETI at home is, I think, like 1 million people at maximum. So astronomy is popular, despite the fact that it has no commercial value at all. Maybe even partly because of that fact. That's, of course, why the data is non-proprietary. Nina McCurdy and I and our colleagues have, especially since starting HiPACC, been feeding beautiful visualizations to planetariums. So we work with the California Academy of Sciences. This is the planetarium at the California Academy of Sciences. It has a big dome, but what's unusual is that it's not directly overhead. It's tilted forward about 45 degrees, so you don't have to lie back in your chair and fall asleep. The Adler Planetarium in Chicago last summer unveiled the most advanced planetarium in the world. It's got 20 new projectors. They're called Zorro projectors. And they're very blacks and extremely brilliant colors. And it's 8,000 pixels across, and it's operated by a powerful computer system. And they wanted to have a bang-up show to introduce their new planetarium capabilities. So we ran a special simulation for them, and I'll show you a sort of small version of that. Probably it'll come tomorrow. I'm not quite sure how far I'll get today. Of course, what I can't show you is 8,000 pixels across in a dome. So what this was the CLUES simulation. That's the Constrained Local Universe simulation. So it's supposed to represent the nearby universe about 64 edge-inverse megaparsecs across, so about 300 million light years across, with us in the center. And the whole evolution of that part of the universe with a Virgo cluster and a Fornax cluster and so forth. So that was done for Adler. And the first planetarium show that's actually going to be about modern cosmology, it's going to be the story of dark matter, dark energy, and why you should take those things seriously, is going to be done by the American Museum of Natural History. That's the Rose Center, the Hayden Planetarium in New York City. And there was just a conference back there to sort of kick off their project, and I was asked to provide another big simulation for them, and we can easily run one. For the one we did for Adler, we ran a 1 billion particle simulation, and we stored 7,200 time steps. It was only 200,000 CPU hours, which for a big allocation is very little. We did it in 2 days. It was 340 terabytes that we dumped in 2 days to a fast disk array. And then we very quickly processed it and produced these images that were a cube. Each side of the cube was 4,000 pixels by 4,000 pixels. And that's what they need to fill an 8,000 pixel across dome. The only problem was that we had to erase the data very quickly. They wouldn't let us keep 340 terabytes on their disk array for very long. So we couldn't really analyze it. So next time, they now have a 2 petabyte array at NASA Ames just for visualization. And they told us that we can keep our for at least a few months the next time we run a big simulation. The reason we stored so many time steps was so that we could do a very smooth animation without having to interpolate. Anyway, and incidentally, that's just 3 minutes, 7,200 time steps at 30 cycles. We also are now developing 3D visualization capability, and a number of other places have this. Stanford, Ralph Kaler is their visualization guru, has done wonderful visualizations. And he actually, when we set up our lab, he sent us beautiful examples to sort of inspire us. And so we're going to be doing this also at Santa Cruz. And a number of science museums and planetariums have 3D visualization capabilities, not in domes. There's only one dome that has this in Hawaii. So that's another thing that we thought would be fun to do. There's a lot of questions about visualization. How best to show 3D structures? Should we do it with fly-throughs, or should we try to do it with stereo, with presenting 2 images to each of your 2 eyes? How do we show gas, stars, and dark matter simultaneously? What's a good visual metaphor? For example, when you're trying to show temperature, for example, of gas, for astronomers, the normal thing would be red is cool, blue is hot. You try to show that to ordinary people, and it flies in the face of their many years of experience with turning on the hot versus cold water. They'll get totally confused. So you have to work out something that works for most people, and especially when you're trying to do something complicated like several different kinds of stuff, stars, gas, dark matter. How can visualizations best convey to non-specialists what's happening? How can we show evolution of structures? Use color, use arrows or trajectory to show motion. How can visualizations be most helpful on the web for planetarians, for teachers at all levels? How can we show the huge range of scales better? How can we show and interact with big data? Matt Turk is going to be giving you some lectures about visualization challenges of this type. And Matt, as many of you know, developed YT as part of his thesis work and has continued to work on visualization. So think globally, think cosmically, act globally, eat locally is the motto in the new book that my wife and I published. It came out in hardback last year, and it just came out in paper. It's called The New Universe and the Human Future. And the reason I'm mentioning it now, besides a little shameless advertising, is that on our website, new-universe.org, all of the illustrations from the book and dozens of astronomical videos, many of which were not made by me, but by people like Volker Springel, are available, and we paid for worldwide electronic rights. So everything's available for download. Of course, proper credit should be given. There's extensive credits on the website for every illustration. And feel free to use these and have fun with them. Well, that's the end of lecture 1, but I see that I still have at least 15 minutes. So let me start lecture 2. I wasn't sure how long it would take to, oh, thanks for turning off the lights. That'll be much better. Actually, it's if you can do it on this side too. Okay, great. Because now I may have time to show some videos, and the less light. Is that still enough light for people to take notes? Okay. So, simulating galaxies in the universe. Now, this is a picture you've all seen. It's the ultra-deep field, Hubble's deepest image in optical wavebands, taken with the advanced camera for surveys. After this image was taken, the advanced camera for surveys broke, and then the astronauts repaired it in the 2009 visit, in addition to installing 2 new instruments. I mentioned the Wide Field Camera 3, which gives us ultraviolet and infrared capabilities out to 1.6 microns, and also the Cosmic Origin Spectrograph, COS. So this is a wonderful image. There's something like 10,000 galaxies there, big nearby ones, but of course, all these faint little dots are distant galaxies, except for this thing, which is 1 star in this image, a nearby star in the Milky Way. The only trouble with this image is that it gives you the impression that this is what there is. What we're seeing is about half of 1% of the cosmic density. That's all that shines or absorbs light. So you can make a picture of the whole cosmic density in this sort of fanciful way. You're supposed to be able to see that there's a pyramid here. I'm sort of outlining the pyramid. Dark energy is about 70%. Best guess now is about 73%. Cold dark matter is about 22%. Atoms are about 4.5%. But 4% are invisible. Presumably some relatively low temperature plasma, 10,000 degrees to 100,000 degrees. Doesn't radiate much because it's extremely low density and very difficult to detect except by tracers like oxygen that might be mixed in with it. And then visible matter, that 0.5%, and that 0.5% is practically all hydrogen and helium. All the heavy elements add up to about 1/100%. And of course, we wouldn't be here if it weren't for those heavy elements. That's what our planet and our cells are made of. About 10% of your mass is hydrogen. You are almost all oxygen. About 60%, 60-some percent of your mass is oxygen. Of course, the most abundant heavy element is oxygen. Second most, carbon. Third most, nitrogen. So we are made mostly of carbon, oxygen, nitrogen, hydrogen. The most abundant elements, except for helium, which of course is chemically inert. So imagine that the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. So here's the ocean, here's the ships. And all we see are the lights on the top of the tallest masts of the biggest ships. Those are the galaxies. Everything else is invisible. So it's dark matter ships on a dark energy ocean. And so in our popular stuff, my wife and I have been advocating that since this is our modern universe picture, there ought to be a friendly name for it. And we propose the double dark theory. Dark matter and dark energy. I used this for the first time in the title of a review article for the German, the newly renovated German journal, Annalen der Physik. And a referee came back and said that this has very bad connotations. So it never occurred to me that it would. So I just checked, I Googled double dark. And for 10 pages, all that comes up is coffee and chocolate and other nice things. Not a single negative connotation at all. Maybe auf Deutsch there's negative connotations, I don't know. But doesn't seem to be the case in English. Of course, the standard name for this is lambda CDM. Lambda for a cosmological constant or some more exotic form of dark energy, and CDM for cold dark matter. A term that I introduced, incidentally, back in 1983. So why should anyone believe this crazy theory that the universe is practically all made of dark matter and dark energy? And the reason is that the agreement with data is absolutely spectacular. By just adjusting 7 parameters, really 6 parameters, one gets a fit to all of this data. And in fact, we already knew before this WMAP data came in what the parameters were. As a matter of fact, back in 1992, in February of 1992, John Holtzman and I had already analyzed the available data before the release in April of 92 of the COBE data, the Cosmic Background Explorer data, and we knew that there are only 2 models of the cold dark matter type that could fit the available data, namely lambda CDM with essentially the current parameters and a cold plus hot model. And we said that before the COBE data was released. After the COBE data was released, they discovered, this is COBE, they discovered this part of the fluctuation spectrum. And they said there's only 2 models that fit the data based on Holtzman's thesis work with me. And so we already knew what the shape of this angular power spectrum of the temperature cross correlations of the microwave sky were. And then as more and more data has come in, we find that there's a superb fit. And the latest data from the Atacama Cosmology Telescope and the South Pole Telescope now has 9 wiggles. Every single data point is in agreement with the predictions. So this is clearly a huge success. So the double dark theory knows about the Big Bang and the cosmic background radiation. But it also fits all the data on the density fluctuations of matter on all scales. Nina McCurdy made this very pretty version of the summary of data from the latest Atacama Cosmology Telescope paper by Holzek. Now, what's the secret of cold dark matter? Why does it work so well? And in particular, where does this spectrum come from? Notice on big scales, it falls fairly steeply. This is many powers. That's 1, 2, 3, 4, 5, 6, 7, 8 powers of 10. Well, 7 powers of 10 across something like 10 to the 12 in length scale, in mass scale, excuse me. And it's shallower on the low mass scales and steeper on the high mass scales. Why is that? What's that coming from? And it's really simple. This is a figure that George Blumenthal and I presented in 1983 as we were starting to work out the details of cold dark matter. And the basic idea is that this is the log of the amplitude of fluctuations, and this is the scale factor, the log of the scale factor. So scale factor 1 is today, log of 1 is 0, so that's today. And this is the early universe, and this is when radiation and matter are making equal contributions to the cosmic density around 40,000 years after the Big Bang. So the Milky Way galaxy comes inside the horizon, that's a 10 to the 12 solar mass dark matter halo, at about 1 year after the Big Bang. So that's 10 to the 12 solar masses. This is 10 to the 9, 10 to the 6 solar masses. But you see, until about 10 to the 15, well, more than 10 to the 15 solar masses comes inside the horizon as the universe expands, the universe is dominated by radiation. And the basic fact is that in Einstein's universe, only the dominant, gravitationally dominant component, only fluctuations in the dominant component can grow rapidly. Basically because if there's an excess in matter fluctuations, but not in radiation, the radiation, it's hardly going to make any difference. What happens is that only when you're in the dominant component does the fact that there's a little extra density in a region mean that that region is going to expand more slowly. And so as the universe becomes overall less dense, that region becomes less dense more slowly. And so therefore, its density compared to average is actually increasing. It's the density compared to average that's increasing is giving rise, that's what's giving rise to this growth. And the fact that all of these scales come inside the horizon when the universe is still dominated by radiation is the key reason why there's this piling up of fluctuation amplitude on smaller scales than about 10 to the 15 solar masses. And then on bigger scales, things come inside the horizon and just grow as fast as they can, and they all grow at the same rate. And so you just repeat, you just take the power spectrum and just increase everything by the same factor. So that's the reason why you get this characteristic shape. The characteristic shape on this previous slide. That's the reason. Now, for some of you, this is blindingly obvious. You learned this years ago. This is basically kindergarten cosmology. But I talked to a few people this morning who are coming into the field basically with background in big data, for example, in geography, who actually may not know this. So forgive me if I'm boring you with the details, but that's the secret of cold dark matter. Now, because the cold dark matter theory, the double dark theory, is so well confirmed by observations, we now study the predictions of this theory for the formation of dark matter structure in the universe and use this to improve our understanding of the visible objects that we can see, galaxies, clusters, and the large-scale structure of the universe. The main reason to do big simulations is to provide all of this data that can then be used to do better studies of the growth and evolution of the entire population of galaxies and of bigger objects like clusters and so forth. So there's basically two kinds of simulations in cosmology. There's dark matter simulations that show large-scale structure, the growth of structure, and dark matter halo properties. And there's hydrodynamic galaxy formation simulations. Hydrodynamic means we're taking into account the cooling and heating of gas and how gas turns into stars and black holes and how the energy output from those objects then affects the future processing of gas and the formation of the actual objects. And so we want to study the evolution of galaxies, formation of galaxy spheroids via mergers and other processes, galaxy images in all wavebands, including stellar evolution and dust. So to start with, the cosmological dark matter simulations. So here's the drunk sitting on the stoop. He says, quarks, neutrinos, mesons, all those damn particles you can't see. That's what drove me to drink. But now I can see them. And you too can see the dark matter because the whole point of the simulations is to make it visible. And the reason I put this in is partly to remind myself to always say at this point that when I show you simulations, everything that's light and bright and colorful is invisible. No stars, no galaxies are being shown, just dark matter. So that's an expanding simulation, a small region of the universe. But notice, focus on the center. It stopped expanding now. This part isn't expanding anymore. That part's still expanding away, but this part isn't. So just to recap, expanding, expanding, expanding. But then, at about halfway to the present, this halo has basically stopped expanding. And in our popular book, The New Universe and the Human Future, my wife, Nancy Abrams, suggested that we coin a new term, two new terms for this, tame space versus wild space. People have heard the term outer space, which just means beyond the Earth's atmosphere. But the really important distinction that a lot of people don't understand is that there's a little bit of the huge cosmic volume which stopped expanding some time ago and will never expand. And that's the part that's gravitationally bound, like our local group, which in fact is contracting. Our galaxy and the Andromeda galaxy are, of course, going to collide in about 3 billion years. So that space has been tamed by gravity. And then in between these gravitationally bound regions is wild space that's being torn apart by dark energy. And that's the distinction people have to understand, so they don't imagine that because the universe is expanding, it's going to be easier to find parking places in the future. So how does a galaxy like the Milky Way fit into this? This is from the beautiful Aquarius simulation by Volker Springel and friends. And this is the Milky Way's dark matter halo. And that is the size of a visible galaxy like the Milky Way. It's, of course, quite small compared to the size of the halo. And presumably, these bright objects will correspond to visible satellite galaxies, except there might be some problems with that. But anyway, how does our galaxy fit in to the big structure? Well, the answer is something like this. So let's look at a region that surrounds a cluster of galaxies. Clusters form where these cosmic filaments, the cosmic web filaments, intersect. So this is a cluster of galaxies from the Bolshoi simulation. So that simulation is about 1 billion light years across. This is a region that's 100 million light years across. That's showing you less than 1,000th of the simulation. So what we're doing is rotating the simulation and moving in closer so you get a better view. What you see is that the dark matter halos on big scales, the massive halos, are quite elongated, whereas the smaller halos are not nearly so elongated. There's good observational evidence that supports this. You also see how the galaxy halos are strung out on these big filaments, and then where the filaments intersect, you get these more massive halos that host groups and clusters of galaxies. So you can populate all the dark matter halos with galaxies, including the subhalos, and compare the distribution with the observed universe. And I know that Darren Croton and Risa Wexler, among others, are going to talk about that in some detail. I'll mention it a little bit in my next lecture. But the result is that there's excellent agreement with observations. That particular video was included in a National Geographic special about a year ago called Inside the Milky Way. And Björk, the Icelandic singer, absolutely loved it. And she asked us for a copy of the video, which we, of course, were happy to give her. So one of her cuts in her biophilia concert tour is called Dark Matter, and she plays this in the background. I was particularly happy that from that same video, the editors of Sky and Telescope saw the same imaging, and they wanted to have me, in the video that's on the National Geographic program, they actually have me in front of this image, and several of the other people from Santa Cruz, including Nina McCurdy, were also in front of it in the TV show. Anyway, so Sky and Telescope's current issue, this is the July issue, has my silhouette on the cover, and this is the that same visualization, except here they put Chris Hensey, the chief visualizer at NASA Ames, put a dark background behind the central cluster halo to make it easier to. And then when the thing is maximally expanded, this central cluster halo completely fills the screen. Anyway, here's the article. It's by Trudy Bell and me. Of course, I introduced Trudy to you earlier. And we were asked not to put this on the web in a publicly accessible place because they want to sell copies of their articles. But there it is. And but when I put this up, when Nina posts this, that'll be a live link. You can just click on it in the PDF file, and it'll take you right to the article, and you can download the article. I have a few copies of the article if people would like them. So this is just the simulation at a number of different times. With nearly 10 billion particles, it's hard to make a video because you'd have to download so much data. I told you we had to do 340 terabytes to make a beautiful video with just 1 billion particles. So do the arithmetic. I mean, this is not practical. So we stored 180 complete snapshots, and we've been analyzing those. But that's not enough to make a smooth video unless you interpolate. I think this is the good time to stop.